In this video, we shall look at a couple of review problems on photoelectric effect. These problems will test the understanding on crucial concepts such as the stopping potential, the maximum kinetic energy of photoelectrons, and the work function. Problem 1. A metal surface has a work function of 5 electron volts. What is the maximum speed of the photoelectrons emitted from the surface when it is exposed to the light with frequency 3.8 times 10 to the power 15 Hz? Let's look at the equation of photoelectric effect. The maximum kinetic energy of the photoelectrons emitted equals the energy of the photon absorbed by the electron minus the work function of the metal. Only when E sub P greater than the work function will the photoelectrons have this much kinetic energy. So let's substitute the details. The maximum kinetic energy of a photoelectron is given by half times the mass of the electron times the maximum speed of the photoelectron squared, equals E sub P is the energy from the absorbed photon, and that is the Planck's constant times the frequency of the radiation, or the frequency of the photon, minus the work function. So solving for Vmax, you get 2 over m times hf minus the work function and square root of all that. So let's substitute the constants. The mass of the electron is given by 9.11 times 10 to the power minus 31 kg. H is the Planck's constant. The value is 6.626 times 10 to the power minus 34. F is the frequency which we are given. It's 3.8 times 10 to the power 15 Hz minus the work function. Note the work function is given in a unit of electron volts, so you have to turn that into joules. So 5 electron volts equivalent to 5 times 1.602 times 10 to the power minus 19 joules. And we have to take the square root of all that. And that will give you an answer of 1.94 times 10 to the power 6 meter per second for the maximum speed of the photoelectron. And that solves the problem. Problem 2. When the ultraviolet light with wavelength 260 nanometers falls on a metallic surface, the stopping potential necessary to stop emission of photoelectrons is 0.2 volt. Calculate the photoelectric threshold wavelength for this metal. What is photoelectric threshold wavelength for this metal? Threshold wavelength is quite simply the largest wavelength the light shining the metal can have that can still produce photoelectrons. So let's again write down the photoelectric equation. It is given by the maximum kinetic energy equals the energy from the photon minus the work function. In this case, the maximum kinetic energy can be expressed in terms of stopping potential as quite simply the product of electronic charge times the stopping potential. The threshold frequency occurs when there is no photoelectrons ejected. It is right at the limit when that happens. So from this equation, that means the threshold frequency is quite simply the work function over the Planck's constant. And since frequency is related to wavelength from this equation, then the threshold frequency can be related to threshold wavelength in a following manner. This is what we are looking for. And as you can see, if you want to calculate this, given these two constants, you need to know the work function. So let's first proceed to determine the work function. We are given the stopping potential, so we can use that information to calculate this. So let's do just that. Using this equation, H is Planck's constant, 6.626 times 10 to the power minus 34 joules second. The frequency can be calculated because we know the wavelength. Frequency is speed of light over wavelength. So that means speed of light is 3 times 10 to the power 8 divided by wavelength, which is 260 nanometers. Turn that into meter, times 10 to the power minus 9. Minus the work function, which we want to determine, equals E. E is the electronic charge. 1.602 times 10 to the power minus 19 coulomb times the stopping potential, which is 0.2 volts. So solving for the work function, this equation will give you work function in the unit of joules as 7.325 times 10 to the power minus 19 joules. Now we can use this value in this equation to figure that out. Why is it important to express the work function in joules? Because the value of H is given to be 6.626 times 10 to the power minus 34 joule seconds, so that is an SI unit. C is speed of light, 3 times 10 to the power 8 meter per second, also an SI unit, so this has got to be an SI unit, which is joules. So let's substitute all the numbers. The threshold wavelength equals speed of light, which is 3 times 10 to the power 8, times the Planck's constant, 6.626 times 10 to the power minus 34 joule seconds, over the work function, which is 7.325 times 10 to the power minus 19 joules. And that's going to give you 2.71 times 10 to the power minus 7 meter, or quite simply 271 nanometers, and that solves the problem. So what that means is if you shine the metal with a light with wavelength greater than 271 nanometers, there will not be any photoelectrons produced. Thank you for watching.